Mastering HDI Stack-ups, unveiling the benefits, applications, and design principles. When it comes to the stack-up structure of PCBs, we can categorize them into three basic types: single-layer, double-layer, and multi-layer. Single-layer and double-layer PCBs consist of only one or two layers of conductive material over the substrate. However, when more wiring space or improved signal integrity is required, multi-layer PCBs become a more suitable choice. Multi-layer PCBs achieve this by stacking multiple layers of conductive and insulating materials to create a complex network of connections. The stack-up structure of a multi-layer PCB typically includes copper layers, cores, substrates, and prepreg. Copper layers serve as the conductive layers, cores provide mechanical support and rigidity, and substrates offer overall structural support to the entire PCB. On the other hand, prepreg is a layer of fiberglass cloth impregnated with uncured epoxy resin, which acts as both an insulating layer and an adhesive layer. During the stack-up process, prepreg is placed between adjacent copper layers or between a copper layer and a core material. Subsequently, under high temperature and pressure, the epoxy resin in the prepreg flows and bonds the layers together, forming a robust rigid board. In traditional multi-layer PCBs, the number of layers can be determined by counting the copper layers. However, when it comes to HDI, high-density interconnect, boards, the stack-up structure differs. HDI stack-ups utilize advanced techniques such as microvias, blind vias, and buried vias to achieve higher wiring density and improved electrical performance. The structure of HDI stack-ups is commonly described as XNX, X plus and plus X, where X represents the number of HDI layers with microvias, and N represents the number of core layers sandwiched between these HDI layers. HDI stack-ups offer numerous advantages, making them the preferred solution for complex electronic devices. Firstly, HDI stack-ups enable higher wiring density by utilizing advanced techniques such as microvias, blind vias, and buried vias. This allows for the integration of more components, signal lines, and power lines within limited board dimensions. Secondly, HDI stack-ups provide improved signal integrity. With shorter and more compact signal lines, they reduce signal transmission delays and losses, while minimizing crosstalk and interference between signal lines, resulting in enhanced signal quality and immunity to disturbances. Additionally, HDI stack-ups contribute to reduced electromagnetic radiation, which is particularly crucial for applications with stringent electromagnetic radiation requirements. Lastly, HDI stack-ups enable smaller FORM factors and lighter circuit boards, which are highly desirable for portable devices, unmanned aerial vehicles, UAVs, and wearable technologies. HDI stack-ups find widespread applications in various fields. One significant area is mobile communication, where devices such as smartphones, tablets, and mobile communication base stations often employ HDI stack-ups to meet the demand for high-density circuit layouts. Consumer electronics products like laptops, digital cameras, gaming consoles, and televisions also commonly utilize HDI stack-ups to achieve miniaturization and high performance. Another important application domain is medical equipment, where highly integrated and reliable circuit board designs are required for medical imaging devices, patient monitors, and implantable medical instruments. The aerospace industry, driven by the need for lightweight and high-reliability solutions, also adopts HDI stack-up technology in aerospace instruments, navigation systems, and aviation electronics equipment. In conclusion, HDI stack-ups play a significant role in the design of multi-layer PCBs. Its high routing density, superior signal integrity, reduced electromagnetic radiation, and compact lightweight characteristics make it an indispensable technology in today's complex electronic devices. Through proper stack-up design, signal integrity can be enhanced and the impact of electromagnetic interference can be minimized, resulting in more reliable and high-performance circuit boards.